Hi, Stu Schwartz of MasterMathMentor.com. This is video AB12A on the topic of transcendental functions. It covers the AB manual pages 58 and 59. Over the years, you studied two different types of functions, algebraic and transcendental. Algebraic functions involve addition, subtraction, multiplication, or division, as well as x with rational exponents. Some examples are y equals x squared, y equals 2 divided by x cubed, y equals the square root of x. But transcendental functions are not algebraic. These functions transcend algebra. And some examples are y equals sine of x, y equals log of x, y equals the natural log of x, y equals e to the x. This video, AB12A, and the next video, 12B, are concerned extensively with logarithms and exponentials. Be honest with yourself. If you are weak in these areas or never really learned them to begin with, take some time to go back in your manual to pages 273 and 274 and review the concepts. We would like to take the derivative of the natural log of x at different values of x, but we really don't know how to. It certainly is not a power rule, nor a product, nor a quotient, nor a trig. So let's see what the calculator has to say. So in your calculator, let y1 be defined as n deriv of the natural log of x with respect to x at x. And then set up a table to find the values of x and the derivative. When we take the derivative of the natural log of x at x equals 0, we get an error. That's understandable because the natural log of 0 does not exist. However, when we take the derivative of the natural log of x at x equals 1, we get 1. At 2, we get 0.5. At 3, we get 0.333. At 4, we get 0.25. And continuing down, at 10, we get 0.100. If you look at the pattern carefully, you will realize that the answers to the derivatives at any value of x is simply the reciprocal of x. So we have a new derivative form called the ln rule. It states that the derivative with respect to x of the natural log of x is 1 over x as long as x is a positive number. The derivative with respect to x of the natural log of u, where u is a function of x, is equal to 1 over u du dx, or simply u prime over u. This assumes that u is positive. Also, the derivative with respect to x of the natural log of the absolute value of u is 1 over u du dx, which is equal to u prime over u. On the next page, we will see some examples of the natural log rule. There are 12 derivative problems on this page, each of which can be solved in 1 or 2 steps. I will be going over each solution rather quickly. If you feel I am going too fast, stop the video and digest each problem before continuing on. In problems 1 through 4, you're asked to find the derivative of the expression using the natural log rule. 1 and 2 are similar. 1 reads y equals the natural log of 4x, so this derivative is simply 1 over 4x times the derivative of 4x, which is 4, final answer 1 over x. 2 is almost the same. Y equals the natural log of x squared minus 3, so y prime is equal to 1 over x squared minus 3 times the derivative of x squared minus 3, which is 2x. Final answer, 2x over x squared minus 3. 3 and 4 are done the same way. However, we can skip a step. We use the fact that the derivative is simply the expression in the denominator and the derivative of the expression in the numerator. So y prime is equal to the derivative of 3x squared minus 5x plus 8, which is 6x minus 5 over 3x squared minus 5x plus 8. In 4, y prime is equal to, the denominator will be the square root of x, and the numerator will be the derivative of the square root of x, which is 1 over 2 square root of x. Simplifying that, we get 1 over 2x. Previously, we had 4 rules: the power rule, product, quotient, and trig. Power was an expression to a power. Product was expression 1 times expression 2. Quotient was expression 1 over expression 2. Trig was some trig function of an expression. Now we add a 5th rule, the ln rule. And this is in the form of natural log of an expression. Just because we have a natural log in our equation does not mean that the form is a natural log. After these instructions, stop the video, and for problems 5 through 12, first determine the form of the problem and then take the derivative. 5 is a simple product rule. So our derivative is the first x squared times the derivative of natural log of x, which is 1 over x, plus natural log of x times the derivative of x squared, which is 2x. Final answer is x plus 2x natural log of x. 6, y equals natural log of x over x is a quotient. We square the denominator, and then the numerator is x times the derivative of natural log of x, which is 1 over x, minus the natural log of x times 1. Final answer is 1 minus natural log of x over x squared. 7 is also a quotient rule, but now we square the bottom, natural log of x squared, and the numerator is natural log of x times 1 minus x times 1 over x. Final answer, natural log of x minus 1 over the natural log of x squared. 8y equals natural log of x raised to the 5th power is a simple power rule problem. So the derivative is 5 natural log of x to the 4th times the derivative of natural log of x, which is 1 over x. Final answer, in the 5 natural log of x to the 4th over x. Number 9, y equals the square root of the natural log of x could be written as the natural log of x raised to the 1/2 power. This is a power rule problem. The derivative is 1/2 natural log of x raised to the negative 1/2 power times the derivative of natural log of x, which is 1 over x. Final answer, 1 over 2x natural log of x to the 1/2 power. 10, y equals the cosine of natural log of x. This is a trig problem. So the derivative is negative sine of natural log of x times the derivative of natural log of x. Final answer, negative sine natural log of x over x. 11 reads y equals natural log of the cosine of x. This is a natural log problem. So the derivative is 1 over cosine of x times the derivative of cosine x, which is negative sine of x. And so the answer can be written as the derivative is negative tangent of x. 12 reads y equals the natural log of the natural log of x. This is a natural log problem. So the derivative is 1 over natural log of x times the derivative of natural log of x, which is 1 over x. Final answer, 1 over x natural log of x. Back in your pre-calculus days, you learned log rules. These were rules for logarithmic expressions which allowed you to simplify them. For instance, the natural log of a times b is equal to the natural log of a plus the natural log of b. The natural log of a over b equals the natural log of a minus the natural log of b. And the natural log of a to the b is b natural log of a. Let us see how using these rules can make the derivative process easier. In 13, we are given y equals the natural log of x sine x. In the direct approach, this is a natural log problem. So the derivative is 1 over x sine x times the derivative of x sine x, which is a product rule. And the numerator is x cosine of x plus sine of x. However, using our log rules, we can write this as the log of a product, which is the sum of two logs. So we end up with y equals the natural log of x plus the natural log of the sine of x. And therefore the derivative is 1 over x plus cosine of x over sine of x. And that turns out to be 1 over x plus cotangent of x. Again, the answers are not similar, but you can take the log rule answer with sines and cosines, get a common denominator, and the answers will be the same. In 14, we have y is equal to the natural log of the square root of x squared plus 2x. The direct approach has us writing it as the natural log of x squared plus 2x to the 1/2 power. This is a log rule. So our derivative is 1 over x squared plus 2x to the 1/2 power times the derivative of x squared plus 2x to the 1/2 power, which is 1/2 x squared plus 2x to the negative 1/2 power times 2x plus 2. The x squared plus 2x to the negative 1/2 can move downstairs, combining with the x squared plus 2x to the 1/2 that's already there. And putting everything together, we get 2x plus 2 over 2 quantity x squared plus 2x. We can factor out a 2, and our final answer is x plus 1 over x squared plus 2x. But now let's use our log rules. We can write this as 1/2 natural log of x squared plus 2x. Taking the derivative, we get 1/2 times 1 over x squared plus 2x times 2x plus 2. Again, factoring out a 2 upstairs, we get our final answer of x plus 1 over x squared plus 2x. I think everyone would agree that using the log rules make things a lot easier, mostly because you do not have to get into these negative exponents. Number 15 reads y equals the natural log of x squared over 3x minus 2. The direct approach sees us using the natural log rule, and our derivative is 1 over the fraction x squared over 3x minus 2 times the derivative of that fraction. That involves us using the quotient rule. We square the bottom, and upstairs we get 3x minus 2 times 2x minus x squared times 3. We have 1 over a fraction, which means that we invert the fraction. And the second fraction can be written as 3x squared minus 4x over 3x minus 2 quantity squared. One of the 3x minus 2's can cancel, and our final answer is 3x minus 4 over x quantity 3x minus 2. But using our log rules allows us to write this as the natural log of x squared minus the natural log of 3x minus 2. And we could even go further, because the natural log of x squared is 2 natural log of x. Now we have two very simple expressions to take the derivative of, and our answer is 2 over x minus 3 over 3x minus 2. No, the two answers are not the same. However, in the second answer, you could write this by getting a common denominator and show that the two answers are equivalent. In 16, we have y is equal to the natural log of the square root of x squared minus 1 over x squared plus 1. I don't want to even consider using a direct approach. It would be writing this as 1 over the square root of a fraction, and then we're going to have to take the derivative of the square root of that fraction. It is far easier to use log rules. First, we write the expression as y is equal to the natural log of x squared minus 1 over x squared plus 1 to the 1/2 power. Using log rule number 3, we can write that as 1/2 the natural log of x squared minus 1 over x squared plus 1. Using log rule number 2, we can write this as 1/2 times the quantity natural log of x squared minus 1 minus the natural log of x squared plus 1. And at that point, the derivative is easy. We get 1/2 times the quantity 1 over x squared minus 1 times 2x minus 1 over x squared plus 1 times 2x. The 2's cancel, and our final answer is x over x squared minus 1 minus x over x squared plus 1. When you see these types of problems on the AP exam, no one is going to tell you to use the log rules. You have to be smart enough to determine that you can do this. In 17, we're told that x squared minus 3 natural log of y plus y squared equals 25, and we're asked to find dy dx. There is no way to solve for y, so we'll attack the problem implicitly. We get 2x minus 3 over y times dy dx plus 2y dy dx equals 0. Multiplying everything by y, we get 2xy minus 3 dy dx plus 2y squared dy dx equals 0. We can factor out a dy dx and write 3 minus 2y squared dy dx is equal to 2xy. And our final answer is dy dx equals 2xy over 3 minus 2y squared. If we wanted to find the slope of the tangent line at any point along the curve, we can simply plug in that point to the derivative. In number 18, we're asked to find the tangent line to the curve y equals 4x squared minus the natural log of 2x squared minus 1 at the point 1, 4. We start by taking the derivative. We get 8x minus 1 over 2x squared minus 1 times 4x. We need to find the slope of the tangent line, so we plug 1 into that expression, and we get y prime of 1 is equal to 4. Since we already are given the point, our tangent line is y minus 4 equals 4 quantity x minus 1, or simply y is equal to 4x. It is always good to verify your answer if you can, and we can certainly graph this function as we see in blue, and we graph the line y is equal to 4x, and it is indeed tangent to the curve at the point 1, 4. That does not complete our study of derivatives of transcendental functions. There is another transcendental function we must consider, and that is y is equal to e to the x. This will be covered in the second half of this video, video AB 12B.